Please welcome Mauro Fasano, University of Insubria.
Okay, thank you very much. I'm proud to nominate Random Power today. So I'm the Deputy Chancellor for Innovation and Technology Transfer at my institution, and I decided to nominate Random Power because they started from basic fundamental research and they were able to understand the value that was in that research. They started from many years ago from a lab in CERN in Geneva, and the next door lab was inventing the web. And now they are providing a cybersecurity solution for that web. So this is Random Power.
Breaking the wall to digital privacy protection. Massimo Caccia, Random Power.
Thank you, Mauro, for the introduction, and thank you, everybody. So, you see, this is a coin, and a coin actually doesn't buy you security. However, it can provide it when you flip it. If you do it once, and you get actually ahead, then the ghost in your machine is maybe, if the animation comes out, yes, it does, the ghost in your machine is setting the value of a binary digit, a bit, to 1. Then you do it again, and again ahead. Then you get a tail, and you set it to 0, and again, and again, and again. By the end of the sequence, you get a string of bits, which is something, actually, that an entity with 2 fingers, whether an alien or a computer, will call, actually, a number. As long as the coin is fair, then the values of the bits is unpredictable, and the number is random. In our digital life, actually, in every security step that is taken is craving for random numbers. Now, the coin actually has a small problem, or a series of. It's a bit slow. It's actually a bit difficult to miniaturize it. And again, it's reasonably easy to make it unfair, to bias it. And this is where it comes Random Power. Random Power was born as a genuine act of serendipity while studying single photon detectors for certain applications. And what we realized actually there was a value behind it because we managed actually to extract the bits analyzing the sequences that we had of pulses that were self-amplified, endogenous generated. What does it mean? That the seating is actually connected to an electron, which in the quantum world is actually crossing barriers like a phantom, in a way that you cannot predict. When it does it, it enters a region of high electric field, then it's getting accelerated and is showering into impact ionization so that you get 1 seed in and 1 pulse within 1 nanosecond out, which is what you just saw here. Now, this is the principle which is by now embodied into this little board, which is a little bit smaller than a credit card. We can do it well. Now, the next step are to design it and to scale it down into a chip for IoT and for mobile, and to scale it up to infrastructural application for making your 5G network secure, which is actually the name of the game, because random numbers, as I said, are the seed, are actually the beginning of the food chain for every step that you take. That is to say, of course, there are easier ways to do it, and especially you can do it through algorithm. But when you do it through algorithm, there's a price to pay. Essentially, the fact that the algorithms are deterministic, so the numbers that you generate are pseudo-number, they're not genuine numbers. And then they can be bugged, and you have problems. Now, this solution is actually at hand. That is to say, you can look at unpredictable phenomena. If you look at classical phenomena, the problem is that unpredictability is due to the lack of knowledge. If you do it on the basis of quantum properties of matter, then it's nature itself which is protecting you from biasing the coin. Well, it has a value in principle. It's about 7.2 billion by 2026 for a total number of deployed devices of 6.2 billion between chips, cards, and systems. So we are a hardware company with an attitude towards making the integration easy. Now, we are not alone, as you can guess by the market. There's a reference company that did well, that was really pioneering about 20 years ago. Now they're part of a Korean giant telecom company. And we do believe that we, little David, can do something against Goliath, especially in terms of simplicity of the system, because they use photonic chips, and also in terms of possibility to integrate it into CMOS technology compliance, that is to say, into standard chips. Now, there are a bunch of other people, of course, on the track. We do believe we are a little bit ahead. Now, you do nothing without a fantastic team, and we are a team of young people of every age, essentially physicists, computer scientists, and say electronics engineers that are coming by our mother university. Mine is on Lake Como, where you have something beside George Clooney visiting us, and the other one is actually in Krakow, in Poland. And we are complemented by people having skills in business and in IP. Never walk alone, and we don't do it. And essentially, these are our European partners with whom we collaborate under the umbrella of Attract that identify random power as one of the projects being funded, 2 million euros. Thank you very much for listening.
Perfect. Perfect. Last second, that was great. No, stay here for the...
I don't rush away.
Yeah, very good. Yeah, you can do that.
My product.
You can do that. Okay, let's straight to the 4-minute questions. The session. Who would like to start? Dear jury, you know I give you the priority, so give me your questions. Yes, Geneviève.
You can ask me random questions.
There's a lot of random number generators out there, and quantum random number generators as well. So how will you differentiate yourself?
We do, because the majority of the random numbers, the quantum random numbers, are actually based on an exogenous source. So they are photonic chips. Essentially, just to make an example, you flash one photon, and then you have, say, a semi-transparent mirror. If it goes straight, you set the bit to 1. If it goes up, you set it to 0. This is a fantastic principle. It works in the lab. It's difficult to embed it into a chip because of complexity. You have the external source. And then because I'm a silicon guy, I tell you there are no two silicon detectors that were born equal. So the sequence of zeros and ones that you get is actually gray, it's not white. And so you have to post-process what you're doing through algorithms. So of course, photonics chips are the next step. But before you get to the stage where you can integrate the functionalities that goes together with the random bit generator into a single die, I think it's a long way to go. What we do, we have an endogenous generation of the pulses, so we don't need external light. And it's fully CMOS compliant.
Thank you. We have a next question here, please. Well, first, Lamine, sorry for the jury. Please, go on.
Thanks. Can you say something about your business model that you're
Our
planning?
business model, as I said, we are essentially hardware developers. So among the partner companies that I quoted, we have people that can support the production. Seco is a listed company that does embedded computer. They will be in charge of the production. And then through the development of the applications, for us, it's not the top priority, comes later. But we have another of the companies, a European level that I mentioned, which is called Kudelski Security, and they are our partners into developing whatever is making the use of our platform easier to integrate.
Next question, please, here at the back.
Yeah, so if I understand correctly, your random number generator is operating at room temperature, right? This is ambient. So do thermal fluctuations, can that impact the true randomness of the generator?
No, it can change the rate because now we are doing, say, trap-assisted barrier tunneling, but we are designing also, sorry, I don't see you very clearly. So, but we are designing also a structure in our silicon die, which is based on direct tunneling. And then we will also decrease enormously, as you probably know, the dependence on temperature. But it doesn't affect randomness. It can affect, obviously, because it's Fermi-Dirac statistics, it can affect actually the rate.
Okay, thank you.
Thank you. Next question, please.
Sorry.
Yes, we have to keep distance. Thank you. Here we go. Stefan, next question. Microphone. Last question. Short.
Do you foresee any difficulties to put your box into the chip? Is that just a technological problem, or do you have a specific one with your technology?
Let me turn the question the other way around. To scale it up into an infrastructural problem is a pure engineering exercise. To move it down into a chip requires integrating in silicon a lot of complementary skills. Obviously, there is always a risk. Now, in the European consortium that we have people that are good in design, a Spanish company, good in making their IP available in terms of security, which is Nagra. We have people like us that are designing the generator, and we have Fondazione Bruno Kessler, they are master in silicon device simulator.
Wonderful.
So this is risk minimization.
Thank you. Thank you very much. We're done with the 4 minutes.
Thank you for listening.
Thanks.